Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on energy balances on single phase non-reactive processes. In the previous lecture, we looked at the introduction for processes which were non-reactive and did not have any phase change. Today, we will talk about such systems where we can perform energy balances to calculate the amount of heat that needs to be supplied or to understand how we can measure the temperature of the one of the exit stream or the inlet stream. For single phase systems, you would have only heating or cooling of the components which are present in the system. So, if you have a single species, then you can directly evaluate change in specific internal energy as integral CV dt and change in specific enthalpy as integral Cp dt, with temperature changing from initial temperature to final temperature or inlet temperature to outlet temperature. For closed systems, at constant volume you would be using delta U's, and for closed system at constant pressure you would be using delta H for performing energy balances. For open systems you would always use delta H dot. So, using the appropriate energy balance equation depending on whether the system is open system or closed system, you would be able to perform all the required calculations. So, obviously calculating kinetic energy, potential energy would be done based on the formula which we already know, and shaft work would have to be accounted for if there are moving parts. If we have more than one component which is being heated or cooled, then the total change in internal energy or enthalpy will have to be calculated as the sum of the internal energies or the enthalpies of the pure components. So, here we are assuming that mixing does not cause any change in enthalpy. As I had already mentioned, this type of an assumption is valid for ideal gases and for liquids which are similar. Okay. Having all these fundamentals in mind, let us perform a few example problems which will help us familiarize ourselves with the concepts associated with this aspect of energy balances. Here is the first example problem. A stream containing 10% methane and 90% air by volume is to be heated from 20 degrees Celsius to 300 degrees Celsius. Calculate the required rate of heat input in kilowatts if the flow rate of the gas is 2 times 10 power 3 liters STP per minute. Now, first thing we need to know is what is STP. STP stands for standard temperature and pressure. According to the latest definition by IUPAC, STP is 0 degree Celsius and 10 power 5 pascals. The earlier definition which used to be used was 0 degree Celsius and 1 atmosphere. So, this has now been discontinued and we have to use 0 degree Celsius and 10 power 5 pascals for STP. Okay. Now that we know this, we can actually calculate the number of moles per liter or the volume occupied by 1 mole of a gas according to STP. So, volume occupied by 1 mole of an ideal gas under STP conditions would be 23.6442 liters. Okay. With all that said, we should also understand why this problem gives the flow rate as liters STP. So, here we have to calculate the number of moles which is coming in. So, this can be done at STP. Although the inlet condition of the gas itself is not STP, this has been given in terms of STP because what it represents is if this gas were to be present under STP conditions, standard temperature and pressure, then it would have a volume of 2000 liters. So, the number of moles can be calculated from here. So, this is just a way of representing molar flow rates. Instead of using the inlet conditions which is 20 degrees Celsius, we would have to use STP conditions to calculate the number of moles of the mixed gas which is entering into the system. With that fundamental covered, let us continue with solving the energy balance. So, this is the system. We have 2000 liters of the mixture coming in at 20 degrees Celsius with 10% methane and 90% air. So, this 2000 liters is the volume if the gas would have been present at STP, and you would have n dot moles leaving at 300 degrees Celsius with the same condition, with the same composition. Now, we need to identify what this n dot would be. Here there are no reactions happening. So, whatever is the mixture which is coming in would be leaving. So, first step is for us to identify what n dot is. So, in this case we already identified that 1 mole occupies 23.6442 liters at STP. So, this implies 2000 liters will contain 2000 divided by 23.6442 moles, which would be, the number of moles would be 84.6 moles per minute. So, this is your n dot. Now that we have the number of moles coming in and leaving the system, we can perform all the other energy balance calculations. So, here there are no material balance calculations required. So, the first step of performing material balances is not required. So, the next step in any energy balance problem is to identify what type of a system it is. So, here it is an open system because we have a flow rate. So, implies that our equation would be q dot minus ws dot equals delta h dot plus delta ek dot plus delta ep dot. Here there are no moving parts. So, the shaft work would be 0. The kinetic and potential energy changes would also be 0 because there is no change in velocity or change in position which has been given to us. So, the equation gets simplified to q dot equals delta h dot. We have been asked to calculate q dot. So, calculating h dot, delta h dot will give us q dot. So, for calculating delta h dot we would have to build the table. So, the enthalpy table has to be built. So, enthalpy table would be built using reference states. So, we need to identify appropriate reference states. So, here we have two components, methane and air. So, identifying appropriate reference states is crucial for performing calculations in a simpler fashion. As I had already mentioned, combustion gases such as air, oxygen, carbon dioxide, carbon monoxide, these which are involved in combustion reactions commonly have a table where you can get enthalpy data from. So, using the reference state from the table would be appropriate for air. So, the table which is there in your textbook Felder-Russo is table B8. So, if we have to use the table B8, we have to use the appropriate reference state from the table, which is gas at 25 degrees Celsius and 1 atmosphere, and methane does not have any such table. So, we would have to use either the inlet or the outlet condition as the reference state. So, in our case we can use the inlet condition which is 20 degrees Celsius as the reference state. So, which would be gas at 20 degrees Celsius and 1 atmosphere. This would be the reference state for methane. Now that we have the reference state for methane and air, we can go ahead and build the enthalpy table. So, we have substances which are methane and air, and the enthalpy table would have n dot in, h cap in, n dot out and h cap out. So, now that we have this table, let us start filling out all the information. We know that 10% of the mixture entering is methane. So, this is the mole fraction. So, the value given is by volume, which would mean that it is also proportional to the mole fraction. So, because of this we can calculate the number of moles of methane coming in as 10% of the total number of moles which is entering. So, this value would be 8.46 moles and air would be 76.14 moles. So, the outlet condition would also be the same with 8.46 moles of methane and 76.14 moles of air leaving the system. So, our reference state for methane was the inlet condition, which means the enthalpy of the inlet methane would be 0, So, our reference state for air was different from the inlet and the outlet conditions. So, both these values would need to be calculated. However, we have a table, so we can directly look it up a table. So, the outlet condition for methane has to still be calculated. So, we have to calculate 3 enthalpies, out of which 2 can actually be looked up from tables. So, now first step is to calculate H1 cap. So, H1 cap, which is the change in enthalpy for a process where the methane goes from reference state to the final outlet condition, which is from 20 degree Celsius to 300 degree Celsius. It would be integral 20 to 300 Cp of methane gas dt. So, we need to look at what Cp value for methane gas would be for this temperature range. So, using the handbook or textbook, we can get Cp value for methane as 0.03431 plus 5.469 times 10 power minus 5 T plus 0.3661 times 10 power minus 8 T squared minus 11.0 times 10 power minus 12 T cube. So, this is the Cp value. So, integrating this from 20 to 300 degree Celsius, we would be able to get the change in enthalpy, which is H1 cap. So, doing that, we get H1 cap as 12.09 kilojoules per mole. From table B8, which is the table in Felder-Russo for combustion gases, the enthalpy data can be obtained. So, H2 cap would be equal to minus 0.15 kilojoules per mole and H3 cap would be equal to 8.17 kilojoules per mole. In case the direct value for that particular temperature is not available, we could still perform a simple interpolation to get the values. So, now we have the values for H1 cap, H2 cap and H3 cap. So, the delta H dot value, which is equal to sigma of outlet Ni dot Hi cap minus sigma of inlet Ni dot Hi cap has to be calculated. So, the outlet is 8.46 moles of methane leaving with an enthalpy change of 12.09 plus 76.14 moles of air times 8.17 minus 8.46 times 0 minus 70 plus 76.14 times minus 0.15. So, this term, whichever is there within the brackets, is the outlet enthalpy, and this in the bracket, the second component is the inlet enthalpy. So, the total change in enthalpy delta H dot is equal to 736 kilojoules per minute. So, substituting this back into the energy balance equation, we would get Q dot equals delta H dot equals 736 kilojoules per minute. The problem asks us to calculate the amount of heat that needs to be transferred in terms of kilowatts. So, Q dot would be equal to 736 divided by 60, which is 12.3 kilowatts. So, the final answer which we are looking for is 12.3 kilowatts. So, this is one example problem where we have calculated the amount of heat that needs to be supplied for heating a mixture from 20 degree Celsius to 300 degree Celsius. So, this is the second example problem. Here we are expected to calculate temperature instead of the heat which needs to be supplied. Let us see how we would approach such a problem. A gas stream containing 8 mole percent carbon monoxide and 92 mole percent carbon dioxide at 500 degree Celsius is fed to a waste heat boiler, a large metal shell containing a bundle of small diameter tubes. The hot gas flows over the outside of the tubes. Liquid water at 25 degree Celsius is fed to the boiler in a ratio of 0.2 moles of feed water per mole of hot gas and flows inside the tubes. Heat is transferred from the hot gas through the tube walls to the water. causing the gas to cool and water to heat to its boiling point and then evaporate to form saturated steam at 5 bar. The steam may be used for heating or power generation in the plant or as a feed to another process unit. The gas leaving the boiler is flared and discharged to the atmosphere. The boiler operates adiabatically. All the heat transferred from the gas goes to the water as opposed to some of it leaking through the outside of the wall. The flow chart for an assumed basis of 1 mole of feed gas is shown below. What is the temperature of the exiting gas? So, this is the flow chart which we have. So, you have 1 mole of carbon monoxide carbon dioxide mixed gas entering, 0.2 moles of water liquid entering. So, which means 0.2 moles of water vapor would be leaving, and you have 1 mole of carbon dioxide carbon monoxide mixture leaving for to be flared. So, this is the system. So, what you see here is the gas will flow only in the region which is white and water will flow only in the region which is grey. So, these small tubes which are present will carry the water, and heat from this gas which is present in the region which is white will get transferred to the water which is flowing in the tubes that are shaded grey. So, because there is so much heat being transferred, water actually heats up, boils and evaporates. So, as I had promised, today's lecture will only focus on no phase change processes, right. However, here we do have a phase change, but we do not have to worry about how to account for phase change simply because we can use steam tables directly. So, here water being heated and changing phase does not affect our calculations as we will be using steam tables. However, if we were to have a phase change for any other component, then we have to know how to account for the enthalpy associated with phase change, which would not be the sensible heat which is supplied. It would not help in increasing temperature, it is the latent heat which would help in changing the phase. We will discuss that in the subsequent lectures, but today we will use this problem just to understand how to perform energy balance calculations. So, the phase change is negated because we are using steam tables. As always, the first step for any energy balance problem is to perform material balances. However, here there are no material balances required because the carbon dioxide carbon monoxide mixture which is coming in does not come in contact with water, and water leaves separately, carbon monoxide carbon dioxide mixture leaves separately, and all the information about the compositions are also known. So, we can ignore any material balance calculations that might have to be performed. So, the next step is to identify what type of a system this is. So, this would be an open system, which means the general energy balance equation would be Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. So, here there are no moving parts, so shaft work will be 0. You do not have any change in velocity or position, so you can ignore kinetic and potential energies changes. In addition to all this, it has also been given that the process operates adiabatically, which means Q dot will also go to 0. So, you end up with a trivial equation which is delta H dot equals 0. So, this is useful because we actually are not trying to calculate heat transferred here, we are trying to calculate the temperature. So, for this, if we have this equation, we would actually be writing the delta H dot in terms of temperature, because we can actually get Cp value in terms of temperature and actually perform integrations, which will give us a polynomial of temperature which we can solve to get the value for temperature. So, let us try to do that. Before that, we first need to identify a reference state. So, what would be the reference states for this problem? So, here we have carbon monoxide, carbon dioxide and water, which are components which we will be using. As I already mentioned, water we will be using the steam tables. So, we need to use the appropriate reference state which is given in the steam tables. So, I have used the Felder-Rousseau steam table. So, we will be using water liquid at triple point as the reference state for water. What about carbon dioxide and carbon monoxide? Here we do not want to use tables because we ultimately have to find out the temperature of the carbon dioxide carbon monoxide mixture which is leaving the system. So, we would have to use one of the inlet or the outlet as the reference state. As we have to calculate the outlet temperature, using the inlet temperature and pressure as the reference state would be the most appropriate thing to do. So, for carbon monoxide and carbon dioxide, the reference state used would be 500 degrees Celsius, gas and 1 atmosphere. Now that we have identified the reference state, the next step is to draw the enthalpy table. So, the enthalpy table for carbon monoxide, carbon dioxide and water vapor can be written. So, you would have N or Mn. So, I am also writing Mn because the value for enthalpy given in the steam tables would be in terms of kilojoules per kilogram. However, the enthalpy we calculate using integral Cp dt would be in terms of kilojoules per mole. So, depending on what units for enthalpy would be, we would have to write the either the number of moles or the mass of the inlet and outlet streams, and you would have H cap in and you have N out or M out, and you would also have H cap out. So, this is the table we have to work with. So, we have 0.08 moles of carbon monoxide and 0.92 moles of carbon dioxide entering the system. We also know that 0.2 moles of water is entering. Because we want to have the enthalpy values in kilojoules per kilogram, we will have to write this in terms of kilograms, which would be 0.0036 kilograms. So, using the molecular weight we can get this mass. So, the outlet streams would also have the same moles and masses because there are no reactions happening. So, you have this 0.92 moles and 0.0036 kilograms. So, we have used the inlet condition for carbon dioxide and carbon monoxide as the reference state, which means these enthalpy values will be 0, and this enthalpy value for water has to be obtained from the steam tables. We have to calculate the values for the outlet streams H1 cap and H2 cap. So, these would be the terms where you would have the temperature term coming in. So, this would be H3 cap and H4 cap. So, H3 cap and H4 cap we can look up steam tables. So, we have information about the inlet and the outlet conditions. So, the inlet condition says water at 5 bar, liquid 25 degrees Celsius, and outlet condition is water vapor at 5 bar and saturated. So, H3 cap would be equal to 105 kilojoules per kilogram from the steam tables. So, here what I have done is I have ignored the effect of pressure because V cap values are actually very small and changes in pressure here is very small. So, from 1 atmosphere to about 5 bar is not too big a change in pressure. So, we can actually ignore the V cap delta P effect on enthalpy. So, for that reason I have actually gotten an approximate value of 105 kilojoules per kilogram from the steam tables, and I will be using this for my calculations. H4 cap can again be looked up steam tables, and this value is equal to 2747.5 kilojoules per kilogram. This is the enthalpy of saturated steam at 5 bar. So, now that we have H3 cap and H4 cap, we can write polynomial expressions for H1 cap and H2 cap, which can then be substituted into the equation which is delta H dot equals 0 to calculate the value for temperature. H1 cap is equal to integral of 500 degrees Celsius to temperature T Cp of carbon monoxide dt, and H2 cap is equal to integral 500 degrees Celsius to temperature T Cp of CO2 dt. So, here we need to know the Cp values for carbon monoxide and carbon dioxide. From any textbook or handbook we can get this value. So, our H1 cap would be equal to integral 500 time to T 0.02895 plus 0.4110 times 10 power minus 5 T plus 0.3548 times 10 power minus 8 T squared minus 2.22 times 10 power minus 12 T cube dt. Integrating this we can get a polynomial which would have the fourth order of temperature. So, then we have H2 cap which would be integral 500 to T 0.03611 plus 4.223 times 10 power minus 5 T minus 2.887 times 10 power minus 8 T squared plus 7.464 times 10 power minus 12 T cube dt. So, this gives us H1 cap and H2 cap. Again, both of these will be fourth order polynomials of temperature. So, now we can calculate delta H dot as 0.0036 times H4 cap plus 0.08 times H1 cap plus 0.92 times H2 cap minus 0.0036 times H3 cap. So, this is the first term which in the brackets is the enthalpy of the outlet streams, and the second term after the minus is the enthalpy of the inlet streams. So, with this equation we would actually end up with a fourth order polynomial of temperature, which would be 1.672 times 10 power minus 12 T power 4 minus 0.8759 times 10 power minus 8 T cube plus 1.959 times 10 power minus 5 T squared plus 0.03554 T minus 12.16 equals 0. So, this is the fourth order polynomial that needs to be solved to get the value for temperature. Fourth order polynomials can be solved using some computational tool. You can do it numerically. So, if you find it hard, you can also assume that the terms which are the higher order of power, which is T power 4 and T power 3, can be ignored because the coefficients for these are in the order of 10 power minus 12 and 10 power minus 8. So, ignoring that, you would not create too much of an error, so which would be still be tolerable. So, you could explicitly state that you are ignoring the higher powers of temperature if you have to perform these calculations manually. As long as you have the computing power to calculate the temperature, then I would recommend using the entire polynomial to get the accurate value. If you were to use Excel or Polymath or one of those software to solve for this fourth order polynomial, you would get the value for temperature as 294.59 degrees Celsius. So, this is the temperature of the exit stream for carbon dioxide carbon monoxide mixture. Now, today we have actually looked at two separate problems which are uniquely different, one where we tried to calculate the amount of heat supplied and the other where we actually looked at identifying the temperature of the exit stream. So, both these can be approached from the same energy balance procedures, and we were able to arrive at the final answers. Hopefully, you have understood the principles behind this, and in the subsequent lectures we will perform more calculations and more example problems to help us fully familiarize ourselves with these concepts. Until then, thank you and goodbye.